We should get started. Should we get started? Should we get started?
Here. Yeah, I mean, I don't know what I'm doing coming up here, but
I mean,
hi, my name is Mathis. I'm a software engineer working for professional leadership. Oh, for the Zoom.
questions
Gotcha.
or anything? But either is fine.
Yeah, I can facilitate that. Thank you, Ajay, for hosting us today. This is very generous of you and MIT as a whole. I'm kind of excited because we kind of discussed about it and I looked you guys up. Excited to see what you set up for us today. And then anyone enjoy yourselves with some pizza, some drinks, and let's
Yeah. Hi, everyone. My name is Ajay, and thanks for introducing me, and thanks for hosting, allowing me to present. So I was a 7th-year grad student up to 2 days ago. I just offended on Wednesday, so I'm officially not a student anymore. But still in this almost the same role. Thank you. So I've been at this place for the last 7 years now, and a lot of my research is about high-performance computing and developing compilers. So I'm part of this group called Commit, which is compilers at MIT. And it is it's general purpose compiler stuff, but we focus mostly on DSLs. And specifically, my research from that is on making it possible for non-compiler experts to write DSLs. And that's completely orthogonal to the fact that I love C++. So I always try to mix those things together. And the research of the 7 years is a culmination of that. So today's presentation is actually not really talking about how to use my research, but just to give a sense of how it works internally. And there's a bunch of hacks we had to do and a bunch of I think they're cool tricks we had to do to make it work. And I feel like maybe some of you would enjoy it too. So bear with me for this hour and a half or 2 hours. Okay, so today's presentation is titled Execution-Based Metaprogramming in C++ with BuildIt. And that might raise some eyebrows because what is metaprogramming and execution-based doing together? So I actually lied about this title a little bit. Don't worry, I didn't lie to the extent that it's gonna it's just the slight difference is that it's gonna be execution-based multi-stage programming in C++ with BuildIt. So this is not really your typical metaprogramming templates, concepts kind of a talk. It's going to be more focused on generating code using code. And I'll talk about that in a few seconds. By the way, I'm recording this talk, so if anyone is not okay with that, let me know. We can mute it when you're speaking. I'll also like to make these talks very interactive, so please feel free to stop me at any point, and I would love to go into more details of particular aspects if they're not clear. And I have hundreds of backup slides, so I can also talk more about it. Okay, let's go ahead. So we love metaprogramming, but what is it really? A few keywords come to your mind when you talk about metaprogramming. Is it template? Is it const expr, const eval, concepts? They're all sort of in the same category, and they let you do compile time evaluation, maybe. They like to write generic code, improves performance. I've heard improves productivity most of the times. Is also for some godforsaken reason Turing complete, but that's good, I guess. But if you have used it for a long time, you know it's very messy and almost like a punishment from God for using this language. I don't want to harp on too much about how bad or good metaprogramming is, but just to give a quick example, and this was a screenshot from Ta's talk here, the last session that we had, and it was an amazing talk getting into details of what cool stuff you can do with metaprogramming. But it is not it's something that takes a lot of time to understand. This particular example, don't try to read it through it, but it's doing merge sort. Apparently, I couldn't follow it entirely till I spent a lot of time understanding it. That's the problem. Sometimes it gets very messy and hairy, and so are the error messages. So I was just working on some code the other day, and I was trying to compile my project, and this is what happened. These are just error messages showing up. The video is 20 seconds. It's 20 seconds of just error messages scrolling on my screen. And I use a wide monitor, so it's not like it's wrapping around. It's a lot of error messages because templates, they just keep on adding. So ideally, we don't want this, right? This is messy. No one likes this. Yeah. So what's a good alternative? We are all C++ developers. and we love C++. So can we just like use C++ to generate C++? That's the question I was trying to answer. So why is C++ great? Because it has mutations. It's an imperative language. It's not a functional programming, purely functional language like Haskell, where you have to completely re-architect your sort of application to behave in a certain way. It can allow external library calls. You can like link against libraries that are already in C++ because it is C++. It has heap allocations, IO, pointer indirection, oops, all the fancy good stuff that we love. But templates specifically has neither of those. Maybe const expr, const eval has mutations in a very restricted way. If you figure out how that exactly works, please let me know. I haven't been able to wrap my head around it completely. But all the nice features that we love, we lose them somehow. So ideally, we want to write C++ all the way, like in the meta stage and also in the the code that we are generating. So keeping that in mind, so we want C++ code generating C++ code generating C++ code. And that's what I'm calling multi-stage programming here. So it's not metaprogramming in the sense like you have a meta program that with some parameters becomes an actual program somewhere inside the compiler. We'll want an explicit thing where you have C++ code that runs and then produces more C++ code. So just to give sort of like a complete block picture of this, let's talk about single stage programming first. The typical workflow that we have, you start with some source code, compile it with your favorite compiler like GCC or Clang, whichever you like, or MSVC, and you generate an executable. You feed in the input and you get an output. This is your single stage programming workflow. What we're going to do today is to generalize this flow. So we're going to say, okay, let's start with some source code, which is a pure C++ source code file. There is no special language. There is no special semantics added. It's a C++ program. And then compile it with your favorite compiler. The way sort of our system fits in, it's a library that gets linked into that first source code. So like you're using a C++ library, basically. And then you compile it with your favorite compiler, and you get an executable. So at that point, you will basically feed in parts of your input into the program. You'll say, okay, like this program takes 10 inputs. I'm going to give you 5 of those inputs right now. And then give me a program that's specialized for those 5 inputs as output. So the output of that executable is literally a string program or a file IO if you want that contains the program for the next stage. You can compile that again, get an executable, feed in rest of the input, and then get an output. Right? So this is like 2-stage programming. You can do this obviously n stages in our system, but for today's talk, let's restrict it to just 2 stages. Okay? Is this workflow clear? Because this is actually a lot relies on understanding this correctly. This is very different from how metaprogramming and templates work, because it is metaprogramming there, but it's like everything is happening inside the compiler. It's very hard to sort of see what's being generated, what's being evaluated. Sometimes it's not even sure if it will be compiled time evaluated or not. This is very explicit in that sense. You're running some code and generating some code. Yeah. So there is a separate compiler here. The GCC or Clang, whatever compiler you're using, is separate from the source code. You just have a C++ program that includes our library, like you have hash include BuildIt at the top, and then you compile it with C++ compiler and get an executable. But the library itself outputs code, which is again source code, like it's producing C++ code again. So I mean, yes, it is a compiler in that sense because it is producing code and accepting a code. So yeah, if you look at this part of the execution, it is a compiler, right? Because source code on the side and source code on the right. So yes, it is a compiler in that sense. Yeah. Yeah, so why is multi-stage as opposed to single stage, right? So typically, when you run a program, it has execution cost, right? It takes some time to run. But now imagine your program has 10 parameters, and say 9 of those parameters are never, almost never changing. They're changing very once in a while. But that one parameter keeps changing a lot. But because that one parameter keeps changing, you have to evaluate the whole program. But what if you partially evaluate that program for those 9 parameters? You'll get a specialized program that's tailored for that specific set of 9 parameters. So you don't have to run the whole program again. You're just running whatever is dependent on that last input. I'll show an example. I think it'll be clear once I show the example.
When you say run, you mean running the compilation?
Running the compilation and the executable produced. So this is a full compilation and execution step. I'll write some source code. I'll say GCC or G++ foo.c++. It'll produce an a.out. When I run the a.out, the output of that program will be a source code, which I can then pipe into a file or directly write to a file and then compile that file again.
So in this case,
the compilation and the execution time in the second stage, because you have already, I'll show an example, maybe it will be clear. The next slide is an example of this. Yeah.
Part of this is part of the run. Like in the traditional thing, only the executable, first one and only executable is the run. Is everything from the first executable over part of the runtime?
That's for you to decide, honestly, because it depends on like how often do you run the first step. Like if you're running it weekly to produce like some source code that tailors, like imagine you have like you're running some service online, right? And you have some parameters changing over every day. You might want to recompile the first or run the first step again to produce a more specialized code once a day. And then every time a new request comes in, you might change the second parameter and generate something. So most of our use cases are of the automated nature, where your build system takes care of all this. You could also do it manually, honestly, because it is just like compiling a normal C++ program. There is no special compiler. So yeah.
So my question is, so you're mentioning how like depending on how the parameters change, like you get out different programs. I guess my question is, how is this better than doing that by like templates? Like templates can also have you specify variables and it can have it.
Absolutely. Yeah, it is exactly. So the mental model is exactly like that. Like when you think about when do you want to partially evaluate for something, it's exactly like templates. Like how we in templates, we provide some parameters at compile time and specialize for those. The same benefits you'd get out of it. The difference is that you don't have to write, like you have all these things available in your first stage. Like instead of writing some nasty enable if somewhere or writing some const expr if, you're writing a normal if, you're writing a normal for loop, you're writing, like you can do pointer in direction. You're essentially running the full C++ language in all stages.
So I guess the benefit is that you don't have to learn how to.
That is one of the biggest sort of use case of our system, because it gives you generics, it gives you metaprogramming, everything in the same syntax and in the same sort of semantics as C++.
This is jumping ahead, but it's another one of the benefits that essentially cache that.
Yes.
Yes,
you're saving on compile time every single time because you've already partially evaluated for some part of it. And now your new compilation will be very fast because it will be like, yeah, on the same lines, simply. Okay, let's actually go to an example. Maybe that will clarify it. Yeah. We'll talk about generics a little afterwards. Let's focus on just like code sort of specialization first, and then we'll get to type specialization afterwards. But let's actually get an example, and then maybe if that answers your question, if not, I'll take them. Okay, so the website the website is BuildIt.so, and sort of like high-level description of it is it's a lightweight type-based MSP library. MSP stands for multi-stage programming here. I just don't have enough space on there. But there's two more keywords here. One is lightweight, and the second is type-based. Lightweight is, I'm just reiterating the same fact that I said before, that it's a library. It's not really a special compiler. It's not a special runtime. It's just like you can apt-get this library and install it and use it. It's a C++ library with its own headers and a runtime library to be linked. And the second part of it is a type-based library. So I showed this example of like multi-stages, right? But how do you decide exactly where, like which code gets evaluated in which stage or which input goes in which stage? And the answer to the question is that we do that through the types of your variables. So in templates, you would write template code versus normal code. Here you're writing just code with different types. So let's look at an example of how that looks like. So here's your sort of like very typical power function that takes a base and an exponent and returns base power exponent, right, using repeated squaring. So there's a while loop there which goes to the exponent and every time halves it and then squares the base and then returns the final value. So now the only slight difference here is I've declared the base as dynamic variable of int. So it's a template, the dynamic of t. And the exponent is defined as static of int. These are the types that the library defines. So everything you write with static var of t gets completely evaluated like a normal C++ code. So all operations, all conditions, all loops get completely evaluated. And everything you write with dynamic variable of t gets produced as it is. So for this particular case, I get this program. So now where does the exponent come from? In the final call there, when you say the context.extract function or return function, it takes the parameters, the static parameters to the function. So this particular function just has one parameter, which is exponent. So that you're supplying here as 15. And so it's saying, give me a implementation of this function where the exponent is set to 15. And so what it does is essentially like this while loop, this if condition gets completely evaluated, and then you get this code, which is all the operations that are happening on the dynamic variable. So this 15, like in this particular case, is a constant put into the source code, but it doesn't have to be a constant. It can be any arbitrary program value. So it can come from the user as an input. It can be like a file input. It can be like an output of some other computation. It's a normal C++ value. So as long as you have a concrete value for that variable, it gives you a program specialized for that. That is the literal output. So I'll show you. I'll take us to like a window where I'll actually run it, and we'll see how it works and how is what I'll be answering to the entirety of this talk. But this is even slightly easier to do. What about if we change it slightly? What if we made the base static and the exponent dynamic? Now the exponent, the conditions like the while loop and the if condition depend on the exponent. So they get produced as it is, like the if condition and the while loop are there. The base just becomes a constant here somewhere. The 15 is the constant here anymore. So it's not very optimized, right? Like it's the same, almost the same code with some constant. But now maybe you can see why this is more optimized, right? Like if you were trying to run this particular program every single time for every base and exponent, you will get some performance out of it. But if you specialize it for 15 and run that sort of with different bases again and again, your performance will be better. No branches, no loops. The division is gone mainly. The division and the modulo are gone, which are expensive operations. You get something very simple. Straight line code that's easy to optimize. Yeah.
Questions. First off, do you benchmark this to see if that actually is faster? And second off, is there a way to make it so that the variable names are something that you can choose that makes more people?
Yes. So I'll answer both of the questions one by one. The first is yes, we have benchmarked this. We have written entire papers on this is my 7 years of research. We have big applications that we have compiled and specialized. For this particular example, if you just run this like base 15, the branch prediction and if conditions don't really, like it actually takes care of it mostly, so it doesn't help. But imagine if you had like a modulo operation happening at every step, because say it was like a modulo exponentiation, that becomes much easier. It actually gains like almost 10x speed up if you do it the right way, like using the specialized version. There are no benches on the right, but sometimes that doesn't matter as much for a small exponent. I'll get one second. And to answer your second question about variable names, so remember, this is a purely library approach. We are not looking at the source code. You could write any variable, and once it's compiled, the variable name is gone. So yes, to answer your question, we don't have variable names, but if you compile your original program with debug symbols on, our library can recover those names and keep those names. I'll show you a live demo of it, and I think that will answer your question. And you had a question. Yes.
But if you do the same thing with metaprogramming, the compiler will take time.
So yes, it's actually this execution now would take 2 compilation and 2 executions. Whereas a normal compiler would, like a single stage would do like a single compilation and a single execution. But what you're gaining out is like the second part of it is running very fast. So imagine you specialize it once and then call it 100 times. You're gaining speed up there. Like you're sort of amortizing the cost upfront. If your exponents, yeah. So we haven't really looked at compile time performance as much because BuildIt itself hasn't been optimized as much for compile time, because as you can imagine, under the hood, that static and dynamic types are a lot of like template mess too. If you were to write it without any BuildIt code to just be like a simple 2 integer function, which will compile very quickly. But because BuildIt itself has a lot of template stuff, that's hard. But this part will compile very quickly because this. That's right. So that's again like that's the exploration space. Like what do you want to evaluate and what do you not want to evaluate? If you're producing 1 million lines, maybe that's a bad idea. But the good thing is you can change that very quickly. If you feel like your code is getting too much sort of partially evaluated, you can change the type to dynamic, and then it will keep the loop as it is. Okay, so let's look at like an online version of how this exactly looks like. So we have this website called BuildIt.so. Try it tab. So this is like, I'm just showing like how the whole system works. This sort of online editor, by the way, in the backend is just running a normal C++ compiler, and it just has like our libraries installed. Like it just has these libraries installed, which is like the BuildIt types. So yeah, all I'm doing is using these types, and then I wrote this same function that I showed before, a power function that accepts base and exponent, base dynamic, and exponent static. Okay. So now this just running this program itself won't give you an output because you just defined a function. You need to do something with that function. So inside the main function, what I'm doing is I'm establishing a context. I'm saying, hey, the BuildIt context. And for that context, I'm saying, here's an entry point to a program. So I'm passing the power function as a parameter. It's a function pointer, but that's an entry point. So it's just like, where do you start executing? Now this function could call other functions, and it can be an entire program. It's just saying start execution here. For the generated program that you get out of it, give it a name power15, because in this case I'm specializing, this is user input. And then here you list all the static variables as parameters. So imagine there were like other parameters here, they should all go here as inputs. And this returns output some opaque object that we'll get into later, but it's basically giving out to you some program representation. And then you just say, okay, we have a code generator. You just say C code generator, here's the AST, and spit it out to stdc out. And that's where the output comes as string. So if I had given this like a file here, it would have gone to a file. But this function is basically, these two functions together take an execution of a program and convert it into code, which you can then spit out. That's like the workflow of it, and then just like manually printing out a main function to call that function again, but obviously this could also be generated. And so now when I execute this program, I get this program that we had talked about before. This main just came from this string I printed out. This is other way of doing multi-staging, by the way, which is by printing strings. But as you can see, that's like more complicated or hard to use. And then when I run this program again, it produces an output. Syntax tree, yeah. Yes. Yeah, so this is not the same as the AST that like the client internally maintains, because we don't have access to it. This is just a library implementation. But we have to somehow represent the program internally in our library, because we do a lot of transformations on it to clean it up, to sort of make it correct. And having an AST representation is good for us. There's multiple reasons, actually. We could have done like a CFG kind of an IR, but that is not as readable. Like once we have to eventually generate code out of it, right? And we want that code to be as close to the original code as possible. And AST representation allows us to do that. Some transformations become difficult, but we saw this is a benefit. And okay, so let's just also quickly change the types to just stress the other implementation where I swap the types around. And then when I run this, it produces the other version. We can also make both static and see what happens, or both dynamic. Let's start with both dynamic first, just and then we don't need this anymore, and we get a version that now takes a while to run because yeah, and then it takes two parameters now because there's both dynamic. But let's see what happens if both are made static. Okay, so let's get there, and then let's provide the first base as say 2, and this was 15. Might be in for a little bit of a surprise still. So we still got some program with unroll, because we still have this one in the middle that's not dynamic. Intermediate local variables also I'm changing now. And now when I run this program, and it just returns, there is no more parameters, and it just returns a constant. Yeah, because we changed everything to static. This program is just behaving like a normal C++ program now. But how is what we'll answer through this talk today. Yeah.
Would it be possible to sort of like in the case where everything is static, have a set BuildIt outputs a function that's constant value, constant expert instead where you could just have that set something?
You mean like to produce a const expert function?
Yeah, or a constant.
You can. So like we have, okay. So once this AST comes to you, you can manipulate it however you want. We allow you to like add annotations. So we have like, if you can add attributes, and you can add like, there's a few operations you can do on the AST before you generate it out, and you can easily add like const eval. You can also extend the code generator itself to add whatever new code generation facilities you want. Right, so that's like one missing argument. So this is where all the not so like nice part comes of it, because it's still a C++ program. Now it says like this template call is provided template. It's C++. So it's going to be, we could clean this up. So we could provide a specialization of this function. So this is a template function internally because it is templated on the type of this function pointer. So we could provide an implementation where it's like missing a parameter, and then we could say static assert. That's all. Like we could improve that. We haven't done that yet. But okay, let's not spend too much time on this. Let's get to like answering the question about how this internally works, if this seems sort of like useful to you. Okay, so that's the working. So how does it work? So first thing is static variables are just like normal variables, right? They get completely evaluated in the first stage. So for now, let's just assume that static var of t equals to t. And you can do that with a simple using like a templated alias. You can just say template type name t using static var of t equals t, right? That should give you the behavior that you want because it's getting normally evaluated. But what about dynamic variable? Dynamic variables they don't actually have any concrete values because the values will come in the second stage. So in the first stage, they're just placeholders. If you have ever written like TensorFlow, PyTorch, you might remember they also have these tf.tensorflow, so it's tf.placeholder values. That's exactly the idea here. We're giving it placeholder values which have their operations overloaded to log the operation instead of actually executing it. So here's an example of this. So this is like a very small implementation of dinvar. It's not a complete implementation. What it's internally saying is the variable has a name and it has like say the plus operator overloaded. So when I do like a dinvar a plus dinvar b, it returns a make plus. So make plus internally is some function which creates an expression or a string, whatever representation you want to use, and that adds to those and then returns it back. And if you chain these function calls now, you get a bunch of expressions. So like if you had a plus b plus c, the first a plus b would evaluate and produce a plus b. Then when that whole thing gets added to C, it will produce that first expression plus that expression, and it will keep on returning that. And somehow we are getting in the direction of like we are creating expressions now by overloading everything. But the problem here is this is a lot of overloading. Like you have to overload, first of all operators. That's fine, that you have to do anyway. But also all combinations of like what arguments can go in there. Like the left-hand side can be a variable, the right-hand side can be an expression. It can be a constant, it can be so many things, right? So that's where like sort of our first trick comes in, which is like not really a trick of our implementation, but like a general C++ trick, I guess, we just use generics. So I'll switch to the, actually, before we go there, I forgot to answer your question about variable names. I thought I was forgetting something. So let's go back to this example for a second. So this one produced, oops. That was an error saying you can't really assign a dynamic to a static because, as you can imagine, that doesn't make. We'll get to that. We have ways to handle that in a very beautiful way. But okay, so this is the output that you normally get. Let's make it back to 15. But we have a support for recurring variable names. So if you just check off this flag here, what this internally does is when you compile this program, it compiles it with -g. So it says like keep around some symbols, and then our library goes into its own sort of debugging information and picks up the name. It doesn't get anything else, just the names of those variables to preserve like this. But you still have to use like _2 and _1 on them, because what essentially happens is like if you have a separate function here which is being called, that function will get inlined. So there might be like multiple copies of the same variable. So to make them unique, we just like suffix it with like a unique counter. So all variables are separate from each other. But we do have a dwarf parser built into it. And the important part is you don't have to deal with it. I had to deal with it. I had to pour through a million lines of dwarf documentation, which I don't know if you know about this, it is a complete like virtual machine built inside the standard itself. It is a very nasty thing to work with. We also actually built a DSL debugger, which abstracts that all away for you. I'm going to talk about that a little bit if there's time towards the end. Right. That can be fixed. So what it's an implementation detail about where that argument comes from. So it only happens for the literal entry points. Any other function call, if you have, like for example, if I had another function here which like say add 1, right? No, let's call it something else. Let's say my arg, right? To give it some name. And then let's say I'm just breaking the semantics here, but like changing the program, but let's say I do this here. It does a best case job of trying to recover the variable names to how much it's possible. Yeah, so oops, it's not able to recover that one either, but give me a second. Let's say there is work being done to make it more robust, but for now it works. So it's preserving that name, but it's not preserving this name. I'll look into it. But yes, the variable names are we have GitHub. No. But please file issues if you see any. I would love to take a look at them. Yeah. So the variable name support is there, but it's improving. So it's different from expression templates in that in expression templates, the operator itself, so okay, in expression templates, each expression that you produce as an output, the type is dependent on what appears on the right-hand side. Like you always write everything using auto, right? Here, everything is dynamic where you do, and you like you can just do a equals to b, where a and b are both dynamic variable of int. The expression value is actually stored inside the variable as a value, not as a type. That's the difference. But okay, so how do we first of all, how do we write all these overloads? So what I'm just quickly going to show how the overloading of this looks like. Also take some time to navigate this repository. So if you look at our repository, there's the headers and the source. So we have include and source. Both of these are organized in the same way. We have blocks and builders, the key components of BuildIt. Block is all the stuff that we use to represent the program. So this is like the AST representation, all the transformations we do on that go into the block directory. And builder is all the magic that construct those blocks. So think of it's like there's blocks and there's builder, and the block are being moved around by the builder. So let's look at the builder operator overload. So here's a bunch of nasty template stuff, but it's basically one operator overloading to handle everything. So we have in the whole system, you won't find another overload for this operator. So for example, we have our plus operator defined here, and it's a simple template operator. So it takes two type name T1 and type name T2 for LHS and RHS, and it accepts literally any T1, T2, but it checks if those are one of our types. So it has a bunch of template checks above, like meta functions that check if it's a dynvar, like here it is. So it checks if it's a dynvar, if it's a builder, like we have some internal types that can appear on the right-hand side, or it checks if it is convertible to a builder, which can be a constant. So we have constructors defined for dynvar from integers and strings and so on. So it checks if it's any of those possible things that can be a builder, and then creates a single overload for all of them. And then the way it does that is by just casting both the left and right-hand side to this one unique type. So all types are converting to that type, and then it just creates a binary operation out of it, which is plus in this case. Not really a trick that you might have not seen before, but the idea is there's a lot of generics inside that take care of the complexity of the whole system. But okay, so that's also a first problem. I think we're getting in the direction where we are able to extract expressions. But this is C++, so it's not a functional programming language, right? You have statements, you have mutations. Mutations are actually fine too, because you have equals operator overloadable, plus plus is overloadable, so that will take care of the effect itself. But somewhere that expression needs to terminate, right? Once you end the statement, it needs to go into the program somewhere. It can't just keep on returning, right? So what we do is the hard problem here is identifying end of statements. Where does the statement particularly end? So what we do is expressions that are not consumed by anything else must be a statement. So if we keep on recursively returning an expression, and that expression is consumed by another expression, the one that's not consumed by anyone else must be casted to void, or is just as a standalone void expression statement. So then let's make it into a statement. So the way that works is, let's take a simple program like this. We have a dynamic variable int v1, v2, v3, like a bunch of them. And so declarations of those variables, like the constructor of v1, like dinvar of int, is also overloaded to produce a statement. So whenever you say dinvar of int x, it produces a statement integer of x, right? So that's what we get here. In the committed statement, like in the produce statements, you get the int x comma y, because the constructor gets called and immediately a statement gets produced. But now what happens is, in the execution, first v2 times v3 will happen because of operator precedence, and then that will produce an expression v2 times v3. Now, as soon as this expression is produced, it gets added to this global object called uncommitted list, where it says, okay, I'm going to hang on to this expression because I have just produced it. No one has consumed it yet. And now when v4/v5 happens, that also gets added to the uncommitted list. But now when this plus gets evaluated, it consumes those two values because it's consuming the return value of those two expressions. Now we go to the uncommitted list and look for them. And we say, okay, these have been consumed, let's remove them. And then instead we add the new expression, which is v2 times v3 plus v4/v5. Further, when you do the assignment overload, that consumes that right-hand side and produces a new expression instead. Now let's just clean up the thing again. And then evaluation goes ahead. We get v7 times v8 gets added, gets consumed immediately. So v6 equals to v7 times v8. We get v9 plus plus, which is also added. And then finally, we reach a new constructor call. This is definitely a statement, right? Like this is definitely the start of a new statement. So everything up to this point which has not been consumed must be a freestanding statement. So that goes into the committed list now, and the uncommitted list is completely clear. And now we're getting sort of like to the point where we can construct statements out of dynamic variables being overloaded. So it makes in very specific ways. So the state is maintained inside the context object. It's not really global, so that context object that you declare, it's inside that. So as long as you use a context object once, it should be fine. But there are some caveats, right? I can talk about that later. Anything can be thread unsafe because we use internal data structures which are not unsafe, which are not safe, so you have to be careful. Yeah. It depends, right? Like, it could be either. Like it's just operators like precedence. No. This is just so okay. So normally in C++ you can overload operators, but you can't change their precedence. They will have the same precedence as the original operator. It will not really lie to it, right? That there's like sub-expression evaluation order is non-determinate. So for a plus operator, you can't say which will happen first, but because star has a higher not associativity. I think it's just precedence, right? Yeah, so precedence, so it will happen before the plus. That's what I'm saying. Like the plus happens after the star and the slash. That's all. Okay, is this clear up to this point? Like what I'm trying to get at, how we extract statements? Okay, great. So let's look at further. Let's look at the whole like setup now. So we have overloaded all the operators. Constructors produce declarations, plus star assignments produce equivalent statements. Function calls have also been overloaded. So if you make a dynamic variable function type, like if you throw in like a function type inside a dinvar, and you call that, it's overloaded to produce a function call. If it's a normal function, it will just get evaluated. Like in this example, where we wrote just add one, that function just got called because it's a normal C++ function. But had I defined this as, let's say dinvar of int add one, but you have to give it a name because it doesn't know what function you're trying to call. So I'm just going to say with name add one. It could be any other name. Actually, let's do. I'll get to that later. So all this is doing now is just declaring a dynamic variable of type int and produce int. So when I call this, it just produces a function call, because the function call on dynamic variables are also overloaded to produce a function call, which is simple. Yeah, it's just like any other operator. In the same way, like square bracket, ampersand, strings being used, all that is overloaded to produce expression of the similar type. So that's what we get on the right-hand side, which is great. so okay. So you'll have to then either convert it to like some static value first, or you have to call dynamic malloc, which would be something like you could define your own malloc, right? Like you could say, if you want to allocate at runtime based on some runtime value, so you could say like run namespace runtime, and then inside that you could define var of void star size t malloc equals builder as global malloc, right? And then what you could do is you could just var in star ptr equals malloc, and then you could use base here. So yeah, sorry, not malloc, runtime malloc. And then you'll get a malloc call in the generated code. I mean, so this is what I mean by external function calls. Like if you have something that you don't have source code for, you can insert like opaque calls into it. And malloc really, there's no point of staging malloc, right? Like there's no point of partially evaluating malloc really. But if you have something else that can be partially evaluated, you can inline that whole code here. Okay, so let's go a little ahead. The next hard problem is this. What happens when I try to like do a if condition on a dynamic variable or an expression, basically anything that doesn't have a concrete value? If it was a static variable, I know if it is either 3 or it is not 3. But what about dynamic variable? They're just placeholder values. And I really can't overload this because C++ doesn't let you overload if statements. It actually doesn't mean anything to overload an if condition either. So what happens here? So the problem is, yeah, we can't identify the start. So, but let's try to solve this problem together. Let's try to like see what happens when I put a custom type inside an if condition in C++. Like what does the semantic and what does the standard say about it? So what I've done is I've just opened a few, let's say, if statements. So I have a empty dinvar class declared here, doesn't do much. No operators are overloaded right now, but imagine everything is overloaded on this, right? And then in the main function, I'm declaring dinvar of int x, right? And then I'm going to do is if x. And then I'm going to say inside this std cout, then called, right? Sorry, keyboard is, or else. So this is normal C++ and normal if conditions, right? Let's compile this. Sorry, I'm just going to quickly show this, and then I just wrote an if condition based on a type that's a custom type, like any type that's not a standard C++ type. Oh, this should be else. My bad. Okay, and now let's compile this. Let's say, what is it? If statement.cpp. We get an error. So what's the error here? It says could not convert x from dinvar int to bool. So that's our first observation. Every time you try to throw some custom type inside an if condition, C++ is implicitly going to try to convert it to a bool and say, is this a truthy value or is it a falsy value? Which branch should I take? So can we somehow like use that to our advantage? What if inside our dinvar of t, we gave it a way to convert it to an if to a boolean? So we say operator bool. Okay, this is a way of converting a particular dynamic variable to boolean. And then let's say return true, right? Let's see what happens. It compiles now, at least it's happy that we're throwing it. And then when I run it, it says then called, because we just told it that this dinvar is a truthy value. What if we change it to false? Else called. So we can use this to our advantage. So let's go back to our slides. So what we do is we overload this explicit cast to bool operator. The explicit is there for very specific cases. If you know about the, yes, they do accept explicit. It's an explicit cast to bool, and we make it explicit because we want to. It semantics says that when you try to branch on a value, it's an explicit cast to bool. Yeah, so okay, so this is what gets triggered. As soon as like you write an if condition, this is what will trigger. So how do we use this to our advantage? Let's look at this program. We have two variables, x and y, x equals to 0, y equals to 1. We start executing it from the beginning. We get x equals to 0 because operator overloading. We get y equals to 1, statements are produced. And then in the evaluation order, first x equals 0 will be produced, which will go into the uncommitted list. And then this explicit cast to bool operator is called. So we say, okay, you're trying to branch on this value. Let's leave a marker here. Let's remember that this is where something happened, and let's try returning true. So our implementation of the cast to bool operator returns true. Execution goes ahead, we get y equals to 2. Because we returned true, the then branch should be taken. Then the z equals to y branch would be taken, and the program terminates. But this is not the complete picture. There is a marker left somewhere which says that we have explored the true part of it. What about the false part? So what BuildIt does, it starts the execution again. Because we gave it a function pointer, right? We gave it a function pointer which can be a lambda, it can be anything. So you can start the execution again. It goes back, it says, okay, x equals to 0, y equals to 1. Oh, hey, I see the same statement again where we had branched before, and there is a marker. So which means we have already tried the true one. Let's try the false one now. So now this operator returns false. We get y equals to 3, z equals to y. And now the entire program is executed. Now what BuildIt does is, with this internal representation that we have, it first converts that point where we had branched into an if condition. It says everything that happened after this point must be under the then part of it, and everything that happened after the else part must be under the else part. And then it also further cleans it up. It says everything that's common afterwards gets merged together, and then you got a program like this, which we generate to be produced in an if condition. Does this make sense at a high level? Yeah.
So this question is like, until you do that, like, you basically end up having sort of like, if you have nested boolean statements, you just act with like an exponential number of like paths, basically until you do the burn.
Thanks for asking that question. So yes, if you have nested if conditions, that actually does have exponential blow up, because you need an exponential blow. If you have if inside an if inside an if, you're potentially like producing 2 power n branches. So yes, you need an exponential blow up there. But the case where it doesn't do an exponential blow up is if we have a bunch of if conditions one after the other. Like you have a if, merge, if, merge. If we do it the naive way that I described, it will keep exploding and like trying all possible. Like what if true of this and false of that, false of this and true of that. But that's where our memorization comes in. So the point where it has ways to figure out, and I'll talk about it later, this merge has happened. And when the merge happens, instead of executing further, it just copies the code from a previous run. So that's where we like actually, the paper has empirical results and theoretical results about this, where it talks about the exponential blow up goes down to linear number of executions and a cubic like time, because you still have to start the execution from the beginning, and each step can potentially require order of n size. But in most practices, like in most sort of programs, it's quadrilateral. It's like square blow up, n power n squared number of branches one after the other. But in extreme cases, it can be cubic. Yeah. Any other questions about this? Yes. So if the program doesn't, oh, okay. No, let's get to the loop part later. If conditions will not ever not halt. We'll talk about loops. Yes. If it doesn't halt, it's undefined behavior. We can produce garbage. No one cares. But that's not the case. Actually, there's parts to it. There's actually layers to it, because once we start doing this multi-stage execution, there's a difference between undefined behavior in the first stage and undefined behavior in the second stage. What if your second stage code has undefined behavior, which you might never reach because it's guarded by a condition that is trivially false? BuildIt will still explore it. Like what if I had x equals 0 and x equals 1? That's trivially false, but BuildIt has no way to know that because it is exploring everything. So what ended up might happening is you might have undefined behavior inside, but undefined behavior in the second code only produces that code. So that undefined behavior is not triggered really. Like if you do a division by 0 under that condition, if you say if x equals 0 and x equals 1, return 5 divided by 0. It will just produce the code 5 divided by 0. It will not actually run that, so it's actually fine. But we'll get to that too. Yeah. No. So okay, in the first stage, if we have optimizations enabled or disabled, it will always produce the same code, because we are relying only on C++ semantics, no C++ optimizations. Like operator overloading is defined the same way irrespective of O0 or O1, O2. So it will produce always the same code. In fact, that's the reason why with -g, we get the same code, we just get the new variable names of it. Yeah. Any questions? Okay, so let's look at how this code looks like in implementation. This is where the nasty part starts. But I'll try to keep it like as simple as like, I don't keep it over like high view because we don't want to like get into details of everything. So basically we have a type called builder, which sort of encodes every, like it's a generic type that can go over expressions or variables. Anything is a builder basically. Anything that can appear inside like the left hand side or right hand side, or in like is a dynamic placeholder value, can be a builder. And this has the operator bool defined. So what this explicit cast to bool operator doing right now is it first commits everything because it's an if condition, which is by definition a statement. So everything by this point, which is not this operator itself, must be, or this expression itself must be committed. So that's gone. And then we just call this function called get next bool from context. So the context that we're currently running under keeps track of like a sequence of bool. So there's basic, and let's jump to the implementation of this one. It should be, sorry, okay, so get next bool, what it's doing is again calling commit uncommitted because I made a mistake. But anyway, it's already empty because we have called it there. But so okay, what this one is doing is internal to the context, it's maintaining a bool vector. This bool vector essentially describes the path that has been taken so far to get to this condition. It's all the previous bools we have returned that got us to this point. And now if, so this statement, this vector starts out to be empty. When you start an execution, this bool vector is empty. So trivially, when you get to this point, the size is empty. So it will throw out an exception. It will say out of bools exception. I don't have any more bools to return, which means I have hit a new condition that I have not seen before. Now, what happens when this out of bool exception is thrown? Let's see where it's caught. So the point of the exception is that it cuts to the user code. So you pass as a function pointer, and the extract function AST calls your function, which calls the operator overloading, which calls this. So now when you throw an exception, it cuts through your code and goes back to our code. Like it goes to the point where it was called from, which is where we sort of like stop the execution, and then we reach here. We say, okay, there was an exception thrown and we are out of it. So now we establish two contexts. We say, let's create true context and let's create a false context. For each one of them, let's create a bool vector, a true bool vector and a false bool vector. First, we copy over the old bool vector. So whatever's choices that have got us to this point, let's copy that over first so we can reach that same execution again, and then add a true to it. And then on the false side, do the exact same thing, but add a false. So now we have two identical contexts that have the same sort of sequence of bools stored inside them, and one has extra true, one has extra false. And then we restart the execution back again, and that gives us two ASTs. We get a false AST and a true AST. They will both sort of first return all the same bools which were before, get to that point, take the two new paths, and then we basically, there's some transformation, which is like trimming at the point where they had branched off, and then we have trim common from back, where we like merge the paths that were behind, and then that gives us the whole AST. And if we do that, and then it creates an if condition at that point, sets the condition to be condition, then to be true AST, false to be false AST, and then returns the whole thing. And this is where all the memoization happens to. So far. Yeah, so imagine you have like, okay, let's go to the program, an example again. Let's take a blank. Sorry. Okay, so let's say then var of int x, right? So I say if x equals 0, and inside let's do, I'm using Vim bindings here for some reason, x plus plus, else x minus minus, and then imagine I have another condition which says if x equals 1, x plus equals 2. Let's say this program, right? So the first time the execution starts, the vector is empty. So it reaches up to this point and it throws an exception. At this point, we create two executions. One gets true added, one gets false added. So the execution starts again. This will take a true now. It won't actually throw an exception. It will take the true path. But then it reaches here and throws an exception because it says this is a new condition I've encountered. But what we do there is we copy over the old vector first. You say, okay, you came using this path. Let's keep that path and add a true to it. So the third execution will have true in the execution context. Then it will come from the beginning, take the true path trivially, take the true path here and produce this code. And because it's recursively happening, they get merged from the back. But the memorization happens along the way. So when the false path runs on this one and it reaches here, it won't actually explore again. It'll just copy over the code from the other executions. That's where the exponential part goes away. The paper has a lot more details about this, but I'm just like trying to give a high level. Yeah. So does that give us at least an intuition of how if conditions are working? And it's implemented in a way that you don't have to worry about nestings. You don't have to worry about like conditions after the other. It just happens. The main idea is you see a condition, we detect a condition by trying to convert a dynamic placeholder into a bool. And at that point, you start the execution again, try returning true, try returning false, get the statements, combine them together, and give a single program. So at this point, I'll sort of use an analogy for this. My advisor likes this analogy quite a lot, which is imagine you're in a maze, right? If you're trying to solve a maze and you're looking at the maze from the top, you have the complete view of the maze. You can solve it very easily, or at least some people can. I can't. But imagine you are in the maze. You don't have a complete picture of the maze, but you have a lamp in your hand, suppose, and you're going through the maze. You try taking different paths. And as you do that, you leave like tokens. You say, OK, I've taken this path, let's try this path, and so on. And eventually, you get a complete picture of the maze. That's essentially what BuildIt is doing. That its view into the program is through this operator overloading. Every time an operation happens, it remembers what's happening. Every time it branches, it remembers what branches it had taken, and then goes back and constructs a full program out of it. What this also means is the control flow that we produce may or may not exactly match what you wrote, but it will behave exactly like it. Like if you write a weird if condition with like, or a loop with some weird continues and breaks, it will behave the same way but produce syntactically different code sometimes. So you had a question? Yeah, let's solve that problem next. Okay, so does that answer a question? Okay, so what's your name, by the way? Spencer?
Yeah.
Okay, so Spencer asked a question about what about loops? How do we detect loops? So let's take the same sort of approach as if conditions. First, you want to detect a loop has happened, and then we have to figure out how to handle it. So what happens if I throw in like, let's take our same sort of like experiment we had done before. While loop, I again have an empty class. I'm going to say while x. I'm going to say std cout running body of loop, right? Let's compile this. Same error, could not convert x from denvar int to bool. So there is really no way to differentiate a loop from a if condition, at least by using this method. And what happens if I define this operator? And let's say return true. What we expected, just constantly keeps running. What if I return false? It never runs, which is what we expected, okay? But this is not enough. Like we couldn't figure out that it actually went back, because the great question you asked was, what if this was like this, right? How do we differentiate those two? You don't want to keep running it forever. There is really no way to know. So now this is where another hack of R comes in, or a trick, depending on how you look at it, is what we call these static tags. I'll explain what static tags look like internally afterwards, but let's for now consider them as an opaque identifier for each statement we produce, which uniquely identifies where this statement came from in the original code. It is somehow magically identifying where this unique statement came from, okay? Now, we annotate each statement with this unique tag. So when we produce x equals to 0, we get 1, like the placeholder tag 1. Then we get x less than 42, 2. And then this is where the branching happens. We try returning true, so we get x plus plus. Then we get z equals x less than 42 again, because we had returned true. So execution goes back. And at this point, because that if condition, like that statement came from the same place, we get the same tag 2. So now I say, okay, we have seen this execution before, and we know that no matter how many times we run again, it's going to produce the same code. So why bother? It uses lim unwind. Actually, it uses we support both unwind or backtrace. But okay, so we say, okay, at this point, let's put a back edge. Let's say this is going to execute in the same way ahead. So the theorem here is code repeating in the first stage is the same as code repeating in the second stage. So we produce a back edge here, and that's it. The execution stops. Then we also do the false path, which produces everything that comes afterwards. And then we get this if condition with a back edge, which is essentially an if and go to. And this is where sort of our post-processing messaging comes in. We then convert this whole thing into a while loop with those body and the statement afterwards. And if possible, also convert it into a for loop if the right conditions match. And this is again where like your exact syntax might not match. Like you might write a while loop, you might get a for loop, you might write a for loop, you might get a while loop. But the behavior will be exactly the same. And then you generate code out of this, and this is what you get. Okay, but yeah.
It's possible to write code where you can get if and then go to the if.
That's perfectly fine. So let's.
No, I don't mean like, I mean in terms of like, is it possible to write first code that generates that?
Let's take it one by one. So okay, let's try. I'll first demonstrate this, and then we'll get to that. So now, if I write this code, and if I say x++ in here, this is a while loop based on x, I get this condition because of. So okay, if you look at it carefully, it is exactly the same code, but because C++ compiler, when it compiled the original code, did loop inversion for some reason to try to optimize it, it basically hoisted one iteration out as an if condition. This is done for like, this is done in very specific cases when the C++ compiler thinks it's necessary, but it's still semantically the same. We do have a UB here, yes, because it is an infinite loop. Actually, no. It works. Let's not overflow. Unsigned has wraparound. Okay, whether uninitialized reads on static lifetime variables or sorry, not automatic lifetime variables is undefined or not is a very debated topic. I think it's not undefined behavior. If it's not taken address of, then it's undefined behavior. Let's get into that later. But anyway, so we get some code like this. But the question here is, what if I had written this using if and like go-tos? Like if I wrote this and if I wrote like if I wrote trash code. Depending on who you ask. It still produces the same code because for BuildIt there is no way to differentiate them. All it sees is like this operator and this operator and this happening again. So it's going to make it into a loop.
Yeah, I guess my question was, is it possible to convince your code to generate this kind of case of like if and then there's a go-to?
Yes, so we have what is called a feature unstructured. So in context, you can set a feature unstructured equals to true, in which case when you run this, it will not convert into loops. And there's a reason for that because imagine there are some very like specific cases. Okay, so this one produces ifs and go-tos. It stops after the go-to extraction. It doesn't do the next passes. And there's a reason for this actually. Actually, there's two things, not just this. Imagine you have two if conditions like this, right? This is it's called not a structured control flow where you have like in middle of the condition, you're going to another condition. If that kind of a pattern, it actually cannot be made into a proper if condition without duplicating the code. So if you have, I mean, maybe I can show, it's essentially this, like if you have a jump going from here to here, and before the jump you go to ahead, it actually cannot be made into a perfectly nested if condition without duplicating the part in the middle. And so BuildIt will like duplicate it for you because all it's doing is executing it, right? So it'll end up duplicating the code in the middle. But if you don't want that duplication, we can ask BuildIt to say, do feature unstructured. I don't care about how the code looks like, but I want it to be like the minimal code possible. So what BuildIt does in that case is instead of actually copying over the code from other executions, it just inserts a go-to that point where it thinks it should go. And that way you can get like some more compact code. In fact, when we generate code for like this DSL for regular expressions, it produces the nastiest code you can imagine, but it becomes actually more bearable because of go-tos being generated. Because essentially a regular expression is a state machine, right? And state machines, if you try to make them perfectly nested, it's going to be very bad. Anyway, so those are like sort of like the more corners of BuildIt that we can explore later, but let's go to the bulk of it. Okay, so does this answer like at least an intuition of how the loops work? I still haven't explained how the static tags actually look like, but So that's where the question was, like, how do these static tags come from? And you had that answer, which is using lib unwind. So one way to know where a particular sort of expression is, or a function call is, or any operator overloading call is coming from, is to look at the stack trace. You can just say, give me a stack trace at this point. And it is essentially a concatenation of the program counters that led to that function call, right? So let's look at the code for that. If you go to the BuildIt source code, src util tracer. So everything about extracting code is extracting stack traces inside this particular thing. We support both unwind, and we also support lib trace. So if you use unwind, it uses like unwind to step through the whole stack, get instruction pointers at each point, and then we sort of insert a special function call in the beginning before calling your function to know where to stop. And if it sees that, it stops. But in the meantime, it keeps pushing all the program counters onto this array. And this unique tag now identifies where a particular sort of expression came from. Does this make sense? There is more to it, but let's ignore that for now. I'll get to that. Okay, so this is the basic idea of how we extract loops. But what happens if we have regular loops? Like, what happens if we have static loops, right? Like, static t is just t. So what if I wrote something like this? For int I equals to 0, I is less than 10, I plus plus. Now, this is not a dynamic variable. It is a normal loop, like a normal loop should run. And if inside this, if I did x plus plus, like imagine this is a static loop, right? Like the exponent case. But because static t equals to t, I can just write t, right? So what happens if I run this code? Oh, wait, I should remove feature unstructured. It defaults to false, so. So we get a while loop, a while one loop even. It just keeps on infinitely going back, at least what it thinks. Because from BuildIt's point of view, it has no way to know that something has changed. Like, it just says, I've gone back to the same place, and everything is exactly the same. The program counters are exactly the same. No matter how much I execute, it's going to be different. But it doesn't know that something has changed, like something, this I has changed, which can potentially stop that execution later, or change the execution, or do something different, right? So now let's see what happens if I do this. Okay? Now we get this. So what's happening is, like, BuildIt needs to be told that there's something that's different, which means that static tags now can't rely just on program counters. They also have to rely on state of all static variables. As long as one static variable has changed, it could potentially change the behavior of execution from that point onwards. So this like step that we talked about, where we said that the tags have gone back, which means I can stop the execution and put a back edge, is only true if static variables are also in the same state as when it was at that state before. So this 1, 2, 3 somehow needs to also encode the state of static variables. So now let's look at the definition of let's look at the definition of how static variables actually look like. So previously we defined them as static t equals to t. Now we can actually make them a wrapper type. So we define static var of t as this class, which internally just has a member of the same type. So it just has a value, a concrete value that holds that t. So this could be integer, pointer, whatever you want. And then we define these operator like conversions to t. So whenever you try to use this static var of t, it implicitly converts to t. So this way you don't need any special operator overloading for this. Like, if you can do plus with t, you can immediately do plus with t. It implicitly converts to that t as required. So this is great. Now this is basically a mimic type. Static var of t is exactly like t. But then what we do is we define these constructors for them and destructors for them, which sort of remember this variable. We sort of maintain a pointer to this variable, which is this, as part of the same context that we're using to run. So the builder context that we had running around, now it sort of remembers that, oh, this variable exists. And every time you try to take a static tag, we actually take a snapshot of all variables and throw it into the static tag. That's where this part comes in, where let's forget about this for now, but this is the essential part, where it goes through all the current context static var tuples. The tuples are it's a pointer to a location and a size, and then it takes a snapshot of that variable and pushes it back into the snapshot. And this snapshot is an opaque snapshot. Think about it like as just an assignment, but internally it's implemented in a way that it supports POD types. So it like looks at the memory, but we can also extend it to like support arbitrary hashes of variables if you support that, or like assignments, or just equals equals. But what this is essentially doing is like it's encoding the state of all static variables into your static tags. So unless all static variables match and unless the program has gone to the same position, it will keep on exploring. And once that happens, you can be sure that, hey, nothing is going to go bad, right? Which actually brings us to some sort of like nice observation, which is that if a first stage variable is actually not being modified, you don't need to use static var. You can just use a normal integer or a normal, like, so this is where like you can optimize this a little bit. If like you had, let's say, static var int y equals to 13, and let's say we are doing x equals to x plus y, right? Like this is, you want the y to be first stage evaluated, right? Right, so if this is not changing, you can actually just remove this. You can say, or for sanities, you can just like add cons to it, but this is perfectly fine. You can have first stage values that are not being mutated. You can leave them out. That actually improves performance quite a lot because you don't have to snapshot them unnecessarily. And this is perfectly valid build-it code. Yeah, so you have three types of values. You have dynamic variables, which are placeholder that produce the same code, static variable that are evaluated in the first stage, and normal C++ types, which are, as long as they're not being mutated during the execution of this function, like entirety of this function, it's perfectly fine to keep those normal variables. Any questions about this? Okay, so let's go ahead. We sort of solved the loop problem. There's a bunch of massaging passes that create loops, parallel loops. Even if you have like annotations on them, we can produce like OpenMP pragma loops. We can even map code to GPU kernels. If we just like call a special function before the loopness that says builder annotate CUDA kernel, the annotation get attached to a loop, and then that loop gets transformed into a CUDA kernel with the right sort of, it gets extracted. You have a nice kernel call inserted, memory gets copied, and so on. So we have like tools to make it more easy to use, but the basic idea is you first need to extract loop and then you can do whatever you want with it. Yeah.
But like, how do you handle like set jump and like jump at all, or do you like just handle it the same way that you handle malloc, where it's just like extra function?
So you can do both. You can have an external set jump and long jump, which will behave like a calling a function, which is perfectly fine. But what if you do set jump and long jump in your code? As long as they're valid set jump and long jump, you're not violating any RAII rules. That is just a normal jump in the code. And BuildIt will not see that. It will just see the operations that happened before and the operations that happened after, which means it will either just like continue the execution from there, or if it goes back to something before, then it produce a loop. This is the same as throwing an exception too. Like if you, in your application, if you throw a exception, BuildIt will just explore that path, and whatever comes after will get inlined at that point. So there is like, you don't need to produce set jumps or produce exceptions. They just get produced as normal control flow. Yeah. Okay, so we solved this. Are we interested in this? What about types that are not basic types? So actually, no one asked me this question, but how do those types actually come from? Like, how do we know if a dinvar of a long versus dinvar of an integer, if it's a pointer, function pointer, how do we get the type from that? So that part is actually very kind of like, as you can imagine, like we have a bunch of specializations for every type. So let's look at this block type extractor, which basically has this base specialization called type namer, and a bunch of templates, but yeah, so type extractor, and it has this extract type function. So it's specialized for all basic types. Like it's specialized for short int to produce the short int equivalent of the expression, and then it's recursively defined for other sort of non-scalar types. So we have a specialization for pointers. So arbitrary pointers can be converted. First, it extracts for the inner type and then adds a pointer type around it and then returns it. For void, for arrays, for function calls, volatiles, all types of things are like recursively defined, so it extracts all type. You might also notice that we have dinvar also as part of it, which means you can do dinvar of dinvar. And when you do that, it produces dinvar. So that's where you get like more than one stage. Let's look at how that looks like. So if I write a code which has dinvar of static var of dinvar of dinvar, whatever nesting you want to do, static var doesn't make sense because it's just static. Like it's this stage, this stage. So that doesn't mean anything. But if I run this code, it produces code with, give it a few seconds, with dinvar and static var, where like the outer static var is being evaluated completely and this one is kept as it is. And then when I run this one, it further evaluates this whole thing and produces some code that looks like this. Like there's some meaning to this. I don't know what it is, but yeah. So we can also arbitrarily nest these dynamic vars and types because they're just types at the end of the day. Should you, if there is an application where some parameters are changing a lot, some are changing maybe less often, and some are like changing very, very less often, there is a benefit to staging it in 3 stages to save execution time essentially. But yeah, so we have things for this, and then we have function types all wrapped up. So we get all basic types can be extracted. But what happens when the user writes this? Like what if I want to do dinvar of foo t, and then I want to do t.x? The problem is dinvar of t is independent of what goes inside it. Like it doesn't depend, like the behavior of t, the members of t doesn't depend at all on what you put inside foo. So how do we magically get that member inside? No, the loops and all is fine. Like no, for the loop, for the condition, for operator overloading, everything, t just behaves like an integer in this case, right? But this part, t.x, how is this even syntactically correct? That was for static variables. That was static. Dynamics are placeholders. They don't really have a concrete t inside. In fact, you can't even construct a concrete t because it might not even be constructible in the first stage. So now how do we handle this, right? How do we inject this x into dinvar of foo? Some of you who might have written C++23 might point to reflection, and you might say, can we reflect on the type t that you pass inside and then create members automatically that behave like that dinvar? That's one way to do it, but we want to support C++11. This is all C++11, by the way. What about inheritance? What if dinvar of t just inherits from t directly? Now what happens? Now there's a lot of if std enable if nonsense there because it's checking, it's only inheriting if it's an aggregate type and not one of our aggregate types, like not an invar-t. Like there's a bunch of checks there, but believe me, it just like, what if we inherit from t? Now magically there's a member called x inside, which will behave like an integer in this case, right? Like it wasn't declared as an integer. But what if we ask the user to also declare that using our BuildIt types? We just say, okay, just use our BuildIt types, but now you can throw this whole structure inside dinvar of foo, right? Now internally inside dinvar of foo, we have a dinvar of x as a dinvar of int x as a member, which we can now overload operators for. So when I do t.x, its operators are already overloaded to produce it, but there's a slight difference, which is that it's not a freestanding variable. So somehow that x needs to be told that it's not a variable of its own. It's just a member of this parent expression, which is t.
The question was, the case where you don't have div bars like S for the struct members, is that just a template error or something like that?
If you don't have a
Like if you have like foo int x, like char star y, rather than foo dyn bar and int x, and like your previous, yeah, that basically. Is that just a template error basically?
like if this dinvar of foo is not defined?
Yeah, so
No, generically defined. It's defined for all types t.
yes, but I guess the question is like when the members of foo are not in bars themselves,
Right. They're just ignored. They'll just be ignored in that case. Because there's no operator overloading on them, they'll just behave like normal values. You can set them to a constant, but if you modify them, then the behavior is undefined. Right? But yeah, so now you have dinvar members, and then this is what you can do. You at least can write this expression. But the problem is if you write this right now, it will just produce like some var 2 equals to 0, right? Because that variable is like a separate variable of its own. It's a dinvar of its own. How do I tell it that it's part of this parent foo without having to explicitly change anything here? Like you could change this by adding some constructor calls here and pass it the parent's address using a special constructor, but that's nasty, which is what a solution we had before. How do we magically tell x that it's part of foo? And especially not just foo, but part of that t specifically. There's no way to do that, unfortunately, because you can keep track of all variables maybe, and then keep track of their ranges and do it, but that's nasty. So let's look at the standard, the ground truth of everything. What happens when there's an initialization? Specifically, this is the point that we want, 2. The order of member initializers of the list is irrelevant. The actual order of initialization is as follows. So when you have inheritance, the constructors are called in a specific order. A direct basis are initialized in left to right order as they appear in the class's base specifier list. So if you inherit from a bunch of types, the constructors of those types are called in the exact order. So can we somehow exploit that? So we enclose this t between public begin and public end. These are like some our own custom types. Now, when begin runs, it stores this pointer onto a stack. When the constructor of t runs, like the denvar of whatever members inside run, they'll first check the stack and see, is the stack empty? If the stack is empty, then it's a denvar of its own. If not, it just remembers that, hey, I'm actually a children of this another variable, and here's the pointer to that variable. And end then pops it off the stack. And now this means you can also recurse this. You can have struct inside struct inside struct inside struct, and they'll all be related to each other. Let's look at how that code looks like. So we have normal constructors look like this. Like you can have a bunch of constructors. We have there's an impl class, obviously, because there should be a constructor somewhere. Oh, we're looking at the wrong file. My bad. Yeah, so this is like a normal constructor that we have. First thing it does is it checks if the parent stack is empty. If it's not empty, then it just takes the parent stack first, and then it increments the member counter. It needs to give it a name, like it has to be member 1, member 0, and so on. And then otherwise it creates a variable by itself. Otherwise it calls denvar of false. And then in the declaration of denvar, where we have, never mind it's called parent selector. Yeah, so we have this is the key part of it. We have member initializer begin and member initializer end, and with a bunch of template nonsense. With the template, we check if it's a class, if it's a base of a variable. So there's a bunch of checks on it, and then finally it does this. It says member initializer begin of t, then std remove reference of type t, and then member initializer end. And the way they are defined is it just does a bunch of casts on that variable itself and then throws it into the stack. So we have at every construction time either it's part of a variable or not. So what does this mean for us in a program? Let's go to a blank one again. I can do this struct foo denvar int x denvar int, or let's say car star pi, right? And then I can simply do when I run this, I get this. So again, names are not available yet. So BuildIt's job is to just create variable names on like type names and member names on its own. And if you do a nested struct, that's perfectly fine too. Like I could do struct bar, which had denvar int z, and then I could just do bar t. Oh, sorry, denvar, you're right. Actually, you can do both. If you just do bar t, then they'll just be inline entirely. They'll just be flattened. But if you do denvar, then it gets an extra indirection. Yeah, sorry, thanks for asking that. So then z dot t dot z equals to 13 produces Oh, sorry. Produces this. But the problem is these structs are not there now. Like, how do you even get access to them? So we have helper functions for them. So as part of the code generation, you can tell us what structures you want to produce code for. So you can say generate struct decal of denvar of, what was it, first bar, and then stdc out, or you could say, oops, let's copy this whole line. Right? And now when I run this, I'll explain how this works too. It's pretty straightforward actually, but oops. Value mismatch. I think it requires a initial indentation. If I remember correctly. Nope. Yeah, I just wrote this yesterday. I didn't stop. Oh, right. Yes, you're right. So let's make it struct bar. You're right. I think the 0 is not required, but I'm going to check. It's been a while. Thanks for catching that. Okay, yeah. So now we get custom declarations and the use of them. So now the code makes entirely sense. So how does this work? It's actually very simple. So we have a options thing that's again a global object which just says whether to track members or not. And when you say track members, what it does is if it's constructing a member as part of a variable, it also tells the parent variable that, hey, I'm actually part of you. Like it maintains reverse references from the parent to the job. And normally this is turned off. Like this track members is usually off. We never use it. But inside this definition for where we define the generate struct decal, we actually do this. So we temporarily turn track members on. We instantiate a dummy object of that type, whichever you asked us for. And now this dummy object has a list of all its members, which we can then iterate through and produce their declarations. So it's just like keeping track of back and forth. But generally this is wasteful, so we don't keep it on. We only keep it on when we're trying to generate declarations. Does that make sense? But there's still a problem with this, right? What about like if I'm calling of external function, like external library? They have fixed types. Like I have to call a type with a specific name. Otherwise, like C++ name mangling, bunch of issues, it will not work. What if I want to give it a name? So we have support for that. Let's go back to our tools. So in this core, what you can do is if you want this struct to be called foo, you just put a special member inside. Const expr static char star type underscore name, which is say foo, right? And what this will do is it will tell the BuildIt system that this variable, this type is supposed to be called foo. Like it's just explicitly telling it the name. And now we get foo. So we can now interface with external libraries. But also each member might need a name, suppose. So you can just do, we have a general constructor for giving any variable a name. Like if you want to give it a specific name, you can just say this. So what this does is just overrides the internal name that we produce with the user's applied name. So then we don't have to do any generation. And voila, we get exact struct that we wanted. And if you want name for this one too, you would do exactly the same thing. If this has template parameters, we have a mechanism for that too. All that works nicely. But in interest of time, let's skip that for now. The what name? That's it. I mean, yeah, sure. I'm not compiling it, just sure. I think it's going to be a problem, but because, yeah, it's better if you just... No, but okay, the generated part is not compiled yet. So that error will only come when we get to compiling that. You can produce incorrect code. That's no one is stopping you from printing bad code. Yeah, but that's how you get like variables with proper names and types and so on. You can also do names for local variables. So if I want this z to be called d, I can also simply do builder with name, and I can say Z. But the thing you have to be careful about, if you do this with name, by default, it skips the declaration. Because this is a mechanism to create like global variables that you know exist in the context, but there is no way to tell BuildIt about it. But if you want the declaration, it has an extra parameter that just says like with decal or without decal. And if you say with decal, then it will produce a declaration too. So it will behave like a normal variable with a name. And then you get fuzzy, everything works from there. Does this make sense? Wonderful. What's the next problem? This is a question that you had asked about before. What happened if we like, okay, so there's two types of values, right? We have static vars of t and we have dynamic var of t. When you try to convert dynamic var of t to dynamic var of t, it's trivial, right? Like it just becomes an assignment. If I try to assign a static var of t to a static var of t, also trivial, it's just a normal assignment. If I try to assign a static variable of t to dynamic variable of t, that just becomes a constant. Like if I do x equals to y, where x is din-var and y is static, it just becomes x equals to 3 or 4 or whatever. But what if I try to do the other way? If I try to convert a static variable, so a dynamic variable, which is a placeholder value, into a static variable, that doesn't really like, doesn't make sense, right? So, but remember, we have already done that for booleans. Like we have already magically converted the truthiness or the falsiness of a din-var to a static boolean, like an actual boolean, through a condition. So can we like generalize the technique in some way? So this actually requires 0 changes to BuildIt. This actually automatically happens by just writing a very simple function on top of BuildIt, like as a library inside BuildIt. So we have, let me show you this, builder util, sorry. So we have a simple utility function called upcast range, which, look at the signature first, let's look at the body later. It takes a parameter, a dynamic variable, a placeholder value, and a range for that value. Like what could this range, like what could be this value's range? But it returns a static variable of t. So signature-wise, it does what we want it to do. Internally, what it's doing is, in a static variable, it's just iterating through that range, checking if that value matches that dynamic variable, and then returns that value. So besides, like if you remove the static variable and dynamic variable, this is just like an identity function. All it's doing is like you give it a value, it iterates through a bunch of values and check if they match, and then returns that value. So this is like returning s, like technically. But nowhere in here is it violating BuildIt semantics. Nowhere in here it's actually assigning an x, like a dynamic variable, to a static variable. It's just comparing a static variable with a dynamic variable, which is perfectly fine, right? This is allowed in our code. So now what happens if I try to use this? Okay, let's take another blank sheet, and let's try to do something nice with it, right? Suppose I have a std, let's say I have an array of integers, 5, 4, some bunch of numbers, right? And this is only available in the first stage, okay? But the user gave me a din-var index as a parameter. I want to index into this array and return the right value, suppose +1. I currently can't just do this would not be valid. It'll produce wrong code, or it will just like violate semantics. But what if I do this? It's util, what's the namespace on it? Sorry, which is builder. Builder. Range of index, and the range for this can be 1, 0, 1, 2, 3, 4. So let's say 4, right? Okay, and then I just need to include the header. Sorry, I'm a little bit jittery today. Oh, it's 4 is not inclusive. Yeah. Oh, sorry. I meant to. We can do both, but yeah, I was planning to do this. But anyway, either is possible. We'll do both. So what if okay, now I write this. What do I get? Sure. Yeah, we'll at 15 minutes away. I think we're almost close to the end. What was the error? Sorry. Return types. We still want to return as a din-var because returning in the first stage doesn't mean anything. So we get a bunch of if conditions, and actually we have a cleanup method for this, by the way. When you get a bunch of nonsense copies, you can just do context dot run RCE equals true. Run RCE is run redundant copy elimination to just avoid like ideal like copies, simple copies. So now we get some code which is like this. Oh, RCE didn't do okay. But anyway, so the idea here is now we get like the variable returning. No, something is wrong. Give me a second. What did I do? Oh, array of index plus 1 should be correct. Oh, not index, sorry, I. I used the Boolean, the didn't to index. So it just had to do like a branch on it because implicitly converts to a Boolean. But this is what we want. Okay, so now this is what we wanted, right? It says if arg0 is equals to 0, then return 5 or return 16, 1, 2, 3, 6, or the last case. So basically now what it's doing is as soon as the branch happens, at this point a static variable is created that is alive. And as long as that variable is alive, all the code that sort of depends on that has access to a concrete value. You can do whatever you want with it as a normal C++ variable and produce code that's different. When that variable goes out of scope, everything will collapse and it'll produce the normal code. But the idea here is like through this magic function, without implementing any new logic inside BuildIt, we managed to convert a dynamic variable into a static variable. Now this obviously has some constraints, like you can't do it for types that are not enumerable, right? But in most cases, it's enumerable, right? Like if you have, even we can write a version that instead of taking a range can take a set, saying it's one of these values, I don't know which, just iterate through them, check for each one of them and return them. But so, okay, normally the users can also do this. They can just write like a for loop and check and do it. But now it's all wrapped up inside this nice function, which after this point, it doesn't care. Like you don't have to wrap the code that comes after. You just have to call this one function. But because BuildIt's extraction mechanisms works like without looking at any code, all it sees is that there is a branching happening here, which led to different code being produced. So that code gets enclosed inside the if condition. Does that make sense? Okay, I'm just gonna try to like quickly go through the rest of the stuff because we are short on time. Let's try to close it at like 8:30, I guess. Okay, so then we have some more examples. This one I would really like to show a lot, but how many of you have heard about the brainfuck language? Pardon my French. Yes, so it's basically this esoteric Turing complete language that has these characters as part of the program, and implicitly it has a tape. The tape can hold like integer values. You have operations like this where plus says, and there's a pointer. So where it says plus increment that wherever the pointer is pointing, increment the value at that cell. The right arrow moves it to the right, the left arrow moves it to the left. The plus minus go up and down. Dot is for printing, comma is for taking an input for that value at that point. But there's this square bracket operator. The semantics of this square bracket operator in the language says, if you see the square bracket operator, check what the current cell's value is. If it's 0, then jump to the closing one. If it's not 0, continue execution. And the square bracket closing says go back to the original square bracket. So now what if I write an interpreter for this language using the system? Let's forget about like types for now. Let's write a normal interpreter. So I have some pointer, I have a PC, I have a tape, which represents the state of the program. Then I have a while loop that goes over the program. For each of them, it does a switch case and says, if it's this, do this. If it's this, do this. Like this is the normal way you would write a brainfuck interpreter. This is the part where it does the square bracket, where it says it's a square bracket, jump to the closing square bracket by finding a closing match, which is defined here, the same thing that you would normally do. Perfect. But now here's the change we do. We change the pointer to be dynamic, which means we want the runtime simulation to keep track of where the pointer is. We want the tape to also be dynamic. But the PC that we are interpreting on, the characters that we're actually interpreting on, are defined as static. Let's see what happens when I run this code. That's using brainfuck. I'm sure there is like a bunch of material on it. But when I run this code, I actually get this program, which is like pure C code now. There is no mention of that variable anywhere. And when I run this, produces hello world because the original mainframe program produces hello world, which is great. Like we essentially converted an interpreter into a compiler by staging the program counter, and which is, if you know about the background, it's called Futamura projections, which we have applied here. But there's a cool part here which goes a little unnoticed usually, and most other staging systems cannot handle, which is this part. So here in this if condition, actually, let's look at the result of this first. So if you look at this original program that we had, it has one while loop, right? It just has one while loop in the whole program. But this generated code, you might notice, has nested while loops. There's a while loop here, and then there is a nested while loop inside here, and there's another while loop here. And these while loops roughly correspond to the square brackets here, like the way they were nested. So how did that happen? Like, where did these extra while loops come from? That comes from this if condition and these PC updates. So here, if you look at this carefully, there's a condition on a dynamic variable. Tape of pointer, both are dynamic. So it's branching on a placeholder value. But inside, it's updating a static value. There's side effects happening on a static variable, which changes the course of how it executes later. What ends up happening is this PC, when you do the square bracket matching and whatever, this PC gets set to a value it had seen before. And because of BuildIt static tags, it just goes back to a point where it says, oh yeah, I have actually seen this execution before, I'm going to put a back edge. And imagine like PC's nested way going back to old values will produce a bunch of back edges, which when BuildIt extracts is going to produce nested while loops. So without having to do any sort of special magic, just writing an interpreter the way you would do, you get some really clean code. Any questions about this? Okay, there's an optimized version of this too, which I like to show sometimes, which is available on the website, where instead of doing the operation directly, we are also just like keeping track of the operator as a static variable. So I'm maintaining two static variables, a last op and a last op count. So because the previous problem we saw that there was like a bunch of same statements again and again, which could be combined into a single one. So what this one is doing is if the last op is not the same as this operator, then actually first evaluate that operator, which goes and does whatever that operation was with the last op count. Otherwise, then just increment the count. If it's the same as the previous one, is the same operation as the previous one, then just increment it by one. So now this is sort of like doing some optimizations in this using, so you're basically using static variables to change the behavior of a dynamic sort of operation, which is fusion in some sense. And when I run this program, you get this kind of a code where the values are being updated in step instead of a single value. You're also, the plus and minus on the pointer is also happening with the steps. But if I run this, it behaves exactly the same. I can also have like, maybe like time to demonstrate, we have var names enabled, then you get code which has, yeah, the tape and the pointer and everything gets preserved so that you can debug and understand your program better. Any questions about this? Okay, since we have 7 more minutes left, let's talk about a bigger application that exercises the system to work. This is like a full, this is one of my last research papers that was published at BuildIt. So it is a full research context. There's a lot of details to it, but I'm going to talk like very high level view of what it is. It's a network protocol compiler. So a while ago, we were working on this networks project where we ran into this issue where to write like very high performance code, you essentially have two options. You have either UDP protocol or TCP protocol. UDP, if I've used it before, is very simple and fast. It's stateless. There are no features really. It's very fast. TCP has reliability, congestion control, in-order delivery, handshakes, and everything. And naturally, it's very expensive to run. Most applications usually need something in the middle. Like they care about reliability, but not about in-order delivery. They know that the network won't be congested, so things like that. And if you need something like that, you are essentially forced to write it by hand. An example of this is like Google developing Quick. They needed some specific features. They hired a team of 100 engineers, and they wrote a protocol of their own. And that's hard to maintain. Like if your constraints change, now you have to go and rewrite the whole system again. So this is an opportunity for using something like BuildIt. So what we did is we wanted to create this core framework, which has a set of minimalistic features. And then everything else, like reliability, congestion control, routing, can be added as like modular blocks onto the system, right? And then even like if you want your own features, you can add them as like new blocks, like encryption at the stack level itself, and plug and create basically whatever ad hoc protocols that you want. So this is actually a great fit for BuildIt because if you think about like, if you imagine like the normal way of implementing something like this, it would be full of overheads. because you have like so much modularity into it, right? Like every time you're checking is reliability enabled, or maybe there's like a function call, like a indirect function call or a virtual function call that describes the behavior of this. Like you can write this in a very modular way to make it easy to use, but that's going to come at some cost. But what if we partially evaluate that modularity of the system itself to produce very optimized code? So that's basically what we do. So we ended up implementing this aspect-oriented programming system, which some of you might have heard this term before, but at a very high level, it's basically we have these paths inside the code, inside the framework, which roughly represent like different things that can happen, events that can happen at runtime. So we have a established path, which is a sequence of events that happen at runtime when a new connection is being established, or a send path, which is a sequence of events that happen when a packet is being sent out. And then on the left-hand side, we have these modules, which can then insert hooks into these paths and change the behavior of that path. So they can say, okay, whenever a packet is being sent out, call this callback function of mine, which, like say, if you're doing reliability, it will add a sequence number. It will keep the packet into some buffer so to redeliver and so on. When a packet comes in, it will send an acknowledgement. So all those kind of things you can insert into them as hooks, right? Normally that would be very expensive, right? So if you have something like this, is an example of it. So you have like the module class at the top, and then you have a hook send, hook receive, hook establish, and so on. And then using a virtual function, you describe what happens inside that module. And then to actually implement the path, you just iterate through all the modules and call their hooks one by one on that path. But this part is very expensive. What if we're using BuildIt? Like let's describe the hooks themselves, so the modules themselves using static variables. But let's describe the actual operations that happen on the packet as dynamic variables. So the hooks accept a dynamic packet and a connection object and then does some operation on it, right? Now, when you iterate through these modules, this virtual function is completely evaluated, which means it gets inline and you get a version that's tailored for your particular code. So when I run this code, I get something like this. You can now further start adding conditions. You can say, if this flavor of reliability do something differently, if this sort of condition matches, do something differently, and you can generate very specialized tailored code for your specific application. And all this happens in a very ergonomic way because you're just writing plain old C++ modules that look like a library. You're getting a compiler, but you're writing a library for a network. So you're not writing like, hey, produce this code for sending a packet. You're just sending the packet. That's the benefit of staging. So using this, we implemented basically a bunch of these modules and a different sort of options for them. And those options then combine together to produce 864 different variations you can produce just by combining those modules in different ways. But there's a problem here, which is these custom protocols also require custom packet layouts. Let's give an example. Imagine you have a protocol like this, which just has 3 fields. It has a source, destination, and length. But now I want to add reliability to it. I have to add a sequence number, right? So the observation here is packet layout depends on features you have chosen. The second observation is, imagine you're deploying for a network which has 4 computers like this. Your protocol can be minimalistic. It can have 2 bits of source and 2 bits of destination. But if you scale up your deployment, now you suddenly have 16 nodes. You need 4 bits of source and 4 bits of destination. So how do you make sure that you can programmatically increase and shape the packets without having to go and rewrite the whole thing? So how is this typically done? So the observation here is packet layout depends on deployment. How is this typically done? Typically, these libraries implement these structures and headers as basically these packed structs, which have members inside them. Like you have a destination, MAC, Ethernet type, and so on. And then when you need to use them inside your implementation, you basically take the packet pointer itself, cast it to a pointer to one of these structs, and then you just operate on the members. You can just say ether type equals to 8080, or you can mem copy into the source and destination. But the problem here is this is not very programmable. Like you can't programmatically remove the checksum field out of this struct. It's going to be there no matter what. You can use templates, but that we know is bad. So the observation here is these structs themselves are just a way of describing to the compiler how those fields are laid out. What if we made that process explicit? What if we turned it into code, and then we already know how to stage code, right? We already know how to sort of control code programmatically. So what we do is basically we create these layout description layers and we create these layout objects, which internally using a very complicated data structure or very sort of complex, not complex, but very heavy duty data structure, maintain properties about each field. So we have a linked list of fields inside your headers. For each field, we define what its size is, what its alignment is, and what its offset is. Offset can be computed by taking the offset of the previous field, adding its size and aligning it to your alignment requirement. And now you can define functions like get value and set value. You can say, now using this alignment and using this offset, and here's the base packet pointer, give me this value. But now when you use this in your module, you can just like programmatically add fields. You can say add this field with this size and so on. And just call the function get packet set packet set value, get value, and so on. And this produces code like this. So all this, because all this is happening in the first stage, the virtual dispatch on the member itself, the evaluation of the offsets and everything is happening in the first stage, you get code like this, which is completely optimized. And now you can just put an if condition here. If you don't want checksum, just don't put checksum, and it's perfectly fine. You're indexing it using a string, so it's type safe too. Like not type safe, but you can check. You can say if that member doesn't exist, throw an error. Now, once you do that, you can also start doing more optimizations. You can say, let's add a function called setRange, which takes a range, a base, and a limit. And then using that compute, like you can modify your get integer function to now do a bunch of bit shifts and a bunch of masking and so on in the first stage, right? But when you run this, you just have to add a single call saying set range 64 to 128. If you know your packet is always going to be between 64 to 128 bytes, you can just call this extra function, and everything else remains the same. But now when the get integer function is called, it produces a bunch of like nice shifts and masks and so on, which depend on the previous fields and everything. So you can have arbitrary properties. Moreover, our system can automatically also rearrange your field. You can say, give me the best packing for these fields. Given alignment and sizes, it can figure out the best packing for you if you want. So using this, basically, we were able to take like a protocol like this, which has a bunch of like, this is like UDP, IP, Ethernet, and so on. We identified some redundant fields, removed them first, like length is there in both of them, so we removed them. There's some useless fields, essentially like version, IHL, TS. These are like things that have been there for a long time and they're there for a reason, but we might not need them, so you can remove them, and you get something like this. And then later on, we can do like the set range optimizations and bring it down to even a small protocol like just 2 bytes with like 3 lines of code by just like setting some ranges here and there, and you get some very optimized protocol, which behaves like your original sort of UDP protocol. And this translates to performance gain. So this graph shows the round trip latency CDF values for 10,000 requests on one of these networks. The two extremes are UDP and TCP. So UDP is on the left-hand side, TCP on the right-hand side. And all these bunch of ad hoc protocols we created, which have like in order, reliability, shrunk, checksumming, and so on, they're in the middle. But they're not just in the middle. They're actually closer to the UDP side. What that means is if you just want that one feature, you could pay just this much cost instead of paying the whole TCP cost. This creates like this pay for what you want kind of a model in your protocol for both features and layouts and everything. And all this is coming essentially because you have staging as a tool for it. If we have a minute, I quickly want to demonstrate like how the system, like adding a module looks like. If that's okay, it'll take like literally a minute. Sorry? It's perfectly fine. You can just link against BuildIt, and that's perfectly okay. Okay, so let's look at this NetBlocks thing. What I've already done for us is today just implemented an empty encryption module. So it just has 2 hooks, hook send and hook ingress. That's all I'm doing here. And then let's look at the implementation of these modules. So currently I just declared the hook. I haven't done anything inside it. It's an empty hook. And then I'm just gonna implement my encryption logic. So let's say for din var int I equals to 0, I is less than payload len, I plus plus. Let's do some very super secure row 32 encryption. So let's say payload of I plus 13 modulo 256, right? This is our encryption logic. And then for decryption, let's just simply do right? The key just gets flipped. And that's it. I just added like 2 hooks into the send and receive part of the code, which does this. And then if I do oh wait, I'll get to it. I forgot one thing, which is also to install this module. So I have this implementation here, so I can just simply now say encryption module of, it's a singleton class, so it just has a single module. Instance.init module. So this init module just inserts the module into the whole path. And now when I run this code, this whole build system will generate all this protocol and everything. And if I look at the generated code, it looks nasty, obviously. But if you look at the send function, you can see that as part of its logic, it somewhere has, oh, sorry, this code here, which does the encryption for us. And then on the ingress path, we have something that does similar decryption for us, but gets in line wherever that send and receive path is done. But let's also look at like the size itself. So the size here is just this expression. But if I change the size declared inside interface module, so we have this computed len defined here, right? I'm just going to add like a range to it, 64 to 128, like I had seen before. And in just one place, I set the range to it. And then here we go. So now this automatically gets some bit masks and additions, some offset being added into it that automatically gives us the right value of it. So by changing in one place, we affected that modules are completely unrelated, but you can define it in one module, access it from other modules, and everything gets changed automatically. So yeah, benefits of staging that can give you like really nice abstractions which are performant and easy to use. So yeah, that's the last slide for now. So what's happening with BuildIt right now? BuildIt is expanding in all directions. It's expanding upwards. We're adding many new applications as we speak. So Breeze is one of our regular expression DSLs where we partially evaluate a regular expression interpreter for the regular expression itself. So we basically get a compiler for regular expressions, and in doing so, do a lot of optimization. So we get like really high performance in very little lines of code. Shim is another DSL that came out of our group that I did not work on at all. There's another PhD student. She built it on top of BuildIt, and it's a compression DSL. So you can write compression algorithms using it, and it generates very specialized code for you. NetBlocks, what I talked about. There's many more actually here, but these slides are a little outdated. BuildIt is expanding downwards. So I didn't talk about this aspect of BuildIt at all. We just showed generating C code. But BuildIt can also generate code for CPUs, GPUs, and recently we submitted a paper for generating code for FPGAs. So from the very same high-level representation with a few sort of annotations by calling some function calls, you can map the same code to GPUs or FPGAs too. There's more examples on our website if you want to look at how to do that. But this basically means that now you can take any of those DSLs and also compile them to a different architecture, giving you like the best of both worlds. And then it's also expanding sidewards. So I didn't get a chance to talk about Detox today. Detox is a companion library that is independent of BuildIt, but also works with BuildIt, where as the execution goes on, it records a lot of debugging information like source locations and state of static variables and records them as data into the generated code. And then when you attach a debugger to the generated code, we have a new set of commands like xlist and xbacktrace and xvar and so on, which you can then use to access those first stage information. And in keeping up with the theme of my whole thesis, which is just hacks on top of hack, that system is entirely implemented without making a single line of change to the GDB compiler system itself. Like everything works with standard GDB. You don't need any special changes. Everything just works by generating some different code that we can directly tap in from the GDB debugger. And then finally, the last thing that I'm currently working on is DBD, or dynamic by default. So in BuildIt, like I said, if you don't use static or dynamic, it's static by default because it behaves like a first stage variable. We have a new system called DBD, which is a compiler tool at this point, like it's a Clang plugin, which goes and rewrites your entire source code to add dynamic everywhere. So everything becomes dynamic. It also converts your like structs into the special forms that you need. Like if it has a with member, everything, so with name, the member, the struct type itself, all those mechanical changes get done for you. So now you can go the other way. Instead of like starting from static and slowly adding dynamic, you can start from dynamic and slowly add static. Because most of the cases you want to keep the code the same, partially valid for a few things, not for most things. So it becomes beneficial to do that. So it's a compiler tool that it's a source to source transformation, takes your source, produces new source, which has dynamic everywhere inserted in a syntactically correct way. And so yeah, this is what I call the Quasar of BuildIt, just because of the way it's expanding, like upward, downwards, and sidewards. And yeah, that's our website. There's a lot more examples on there. There's like the repos are linked, all the papers are linked. My other research that's not BuildIt is also linked from there if you go to my website. But yeah, that's the end of the talk today. And thanks. And we have some swag. I have stickers and keychains for BuildIt in case you guys are interested, I'm gonna just maybe put them there. But I'll take questions now if there are any. Um, So I didn't get a chance to talk about that, but we talked about this example of like this if conditions on like, okay, so you can do a lot of staging using proc macros or by like you can, like TensorFlow has this notion of like if conditions are done using lambdas where you make an if operator that takes in a condition, a then lambda and an else lambda, and you can extract code that way. But there's a problem there, which is the way you would extract code there is like you would run the then part, extract its code, then run the else part, extract its code, and stitch it together. But what if you have side effects on the first stage variables inside the then branch? It actually ends up leaking into the else branch, which changes program behavior. So think about that brainfuck example, that if condition your PC update will happen even in the else part, which will give you a completely different program. But this approach of running it from the beginning and like re-execution actually gives you a new form of metaprogramming that actually no other system supports really. So yes, you can do it in Rust, like this whole implementation, but it would look more or less like this. Like it.
That was more what I meant, not like a difference in implementation, just the fact that proc macros get deloaded by the compiler itself. And so instead of having to like run a program and then run another program, just run the compiler.
But there's a difference there. I think that the proc macros themselves, there's a limitation still. You cannot do everything with proc macros. You ideally want the host language entirely available. You can like, one of the benefits there is like in our code, in the first stage, you can call an external library that you don't have source code available for, as long as it's purely static. But with proc macros, you have to rewrite the whole thing as proc macro. So that's the benefit of doing it like this way, really. But yeah, I mean, obviously, we can implement this whole system in Rust because, as you notice, nothing of this is like specific to C++, except for all the hacks that we had to do. But the ideas are transferable. In fact, we're working on an implementation of this for Python, where the whole ecosystem is available in Python. It's work in progress because apparently a lot more people care about using Python. But the cool thing we did is we still use the Python sort of like front end, but once the AST is extracted, we can also produce C++. So you can write Python and get C++ out of it if you care. It's a little tricky because types need to come in from somewhere. So we require like type annotated Python, but yeah. But anyway, yeah. Any more questions? I'm happy to chat, but yeah. Yeah.
If I understood it, a lot of the specialization is based on giving the explicit value stat.
Yes.
Or potentially this several specific.
Right.
Have you thought about generalizing it to give other types of attributes, potential ranges, you say A is always 5 times B?
Yep. Yep. Yeah. So I didn't get a chance to talk about like more applications of this today, but essentially, the idea there is you can pack dynamic and static values together, where static values keep track of meta-property or other properties about dynamic variables. So like things like this dynamic value, I don't know what the concrete value of it is, but I know it's between this range. Or I know that for now it's a constant, it might not be a constant later. And we do that a lot in our program to like sort of do like first stage optimizations, where you're like, you can do data flow analysis essentially entirely. Yeah. Like you can keep track of which variables, like for the case of like GPU stuff, we keep track of whether this data is residing on CPUs or GPUs, so we can move it as required based on where it's used. But yeah, you can essentially do like a lot of like tracking of properties about unknown values using these known values. But that doesn't require any changes to BuildIt itself. Like you can do this on top of BuildIt. And users do that by like packing structs together, which has like a dynamic variable and a accompanying static variable. In fact, the brainfuck example I showed, that's doing exactly that, right? Like the last op and the last op count is keeping track of some properties about those dynamic operations without actually doing them. And then later on checking them when required. So you can do that. Yeah, it's possible. A constraint solver, so like a linear programming solver, maybe.
Like if somebody writes a quadratic equation involving static bars and dynamic bars.
Absolutely. So that's that exact problem. So we ran a hackathon for the system in a school back in India, in a university, where the students learning compilers for the first time interacted with this, and one of them actually worked on a quadratic. It was a general polynomial evaluation and also solving, I think, if I remember correctly, where they the simplification of the expressions happened in the first stage, but the evaluation happened in the second stage. So the variable values were known later, something on those lines. You can implement something like that. So the idea essentially is, what do you want to specialize for? Like for the structure of the constraints, yes, that's beneficial. The values themselves can come later. Yeah. Thank you so much. Yeah.
Very entertaining.
I'm glad. These slides I have never done before, so I'm happy. Thanks.
Best of luck with everything and keep us in touch.
Absolutely. I'm going to stop recording this for now.